All right, this is just my concept. It wouldn't take long to figure if it's going to work or not. If we can harvest more energy here than we started with here, then we should proceed. If not, we should just forget about it. But if we're sending light through here with a laser, and you have to experiment. You can't do this in 10 minutes, or you might be able to in 10 minutes. But it's shooting through here, through a venturi, and the starting, let's say it took 5 watts of energy to get this laser to go. And they don't take much energy whatsoever. And if we could come out of here with 500 watts, 100 times more, that would be pretty good. Because then you could take that energy, feed back to keep this going using part of it, and the rest you feed off. And I'll show you something you might even be able to carry around in a little lunchbox. Because what you're going to get here, you have to harvest right there. You got to harvest it right there before it comes back to the black. And then it will go anywhere you want it to go through wires and so forth to get back to another bunch of black. That's all the white wants to do. It will seek black like a rocket ship. That's why electricity, well, lightning. Lightning is nothing more than the white part. Right to ground. It'll go right through you. You put your hand up and right through you, you turn into ash. This stuff is just deadly powerful. A good, strong motor with electricity just is unbeatable. Very, very powerful. But you have to be able to get straight to that white. And again, it has no weight whatsoever. This event right here that I'm showing you, I'm going to show you an atomic bomb blast. This is literally exactly what happens in an atomic bomb blast. It's so powerful that the white is pushed forward ahead of the black particles. They're separated at this point. All the white is ahead of the black. Well, not all of it, but most of it. And that's the wave that's pushing this out. This is just like an atomic bomb. Now, there's going to be a house right here. And we're going to see it in slow motion. And the house is going to vaporize. It's not going to move. It doesn't move whatsoever, not even the tiniest bit of movement. It's just smoke comes up, and then all of a sudden the black hits, and boom, it's all over. I'm going to show you that. This was from the nuclear bomb blast. And some of that footage is, oh man, is this stunning. All right, just to get your interest, I think we might be able to get free energy. And here's the deal. If you can create electron showers, these showers, you can create excess energy. You come into these low energies, and then it goes right through the roof. You see the showers? This is the number of electrons. They come in like this, and then they shower way up to here at the venturi, which gives you an enormous amount of energy. And this is all recorded. I'm not making this up. They understand this. They just don't know how to do it. We did it using the venturi. And I think this little venturi, and having thousands of them, literally, because the laser is just tiny. It's just a little laser light. Tiny. You could have strips and strips and strips of them, and then you have the receiver on the other side, which would have to be on like a copper plate or something with all this thin film on there, absorbing this energy somehow, and then shoot it down through a photodiode bus, basically, into, a little bit of batteries. You don't need much battery. I wouldn't think. You could just use it. Because what this is going to create is what's called potential energy and kinetic energy at the same time. And then, but you just have to feed it back through your devices or wherever you want it to go, back to the floating ground. Everything uses a floating ground. All handheld devices use a floating ground. Otherwise, it goes right to earth ground. We don't need that. We have a floating ground. Everything that you have with a handheld device has a floating ground. That has a floating ground. And that's the laser we used to do these experiments. This is very simple stuff. If it works, you could walk around with something like this, plug in any device you want, any type, any kind. We have regulators in there, very simple stuff, and very moderate. I mean, everything's already designed and built and ready to go. It's off-the-shelf stuff, basically. Now, there's a lot of design characteristics for the venturi, yes. that could be done. We need all that stuff is very simple for somebody who really knows what they're doing. I'm beyond this now. I'm out of it. I do understand it, and it's all based on my original theory about atomic vapor. And that's what we have, atomic vapor. And you need that white. That's the vapor part you need. It doesn't have any weight whatsoever to speak of. The black has all the weight. And that's what we want to get back to, the black, which is the floating ground. All right. I got hiccups, so if you hear a hiccup, don't worry about it. Now, these are the neutrinos. There's black ones and white ones, basically. And as they move through the air, they gain energy and become color. Okay? This one is the muon, the black one. Never changes. There's no color to that. This is one here takes on the color. Okay, here's what's going on in space. You got the sun. It emits radiation. We know that. It's warm. It hits us. It makes solar panels conduct electricity. It's heat, it's energy, and it also conducts dark matter along with the white matter, and they spin according to their speed towards the Earth. Now they will bump into things in a way because there's all kinds of hydrogen out there, saturated with hydrogen, and all the little particles that are coming off the sun and from every luminous body, they're everywhere, saturating our universe. They don't take that into account with the Webb telescope, Webb or Hubble. They just say, oh, it's got to be 600 million years away, 10 billion zillion years. No. Light slows down as it approaches because there's all kinds of particles here. It's just, I have shown you or will show you the fields in space that they have to navigate. It's quite obvious that space is saturated, and even Fermilab, Don Lincoln says, yes, there is no vacuum in space. It's totally saturated with particles, and they blink on and off as they're getting stimulated by the light. It's millions of degrees out here, and 10,000 on the surface. No explanation for that whatsoever. It's, oh, it must be getting hotter out here for some, because of fusion. Well, why? It would be hotter here and get less hot out there, because they say this is just a vacuum, there's nothing out there. No, it's saturated. And the reason this is getting so hot way out at the corona, don't forget that's the surface, way out here at the corona, it's millions of degrees. And that's the reason, because it's scrubbing and spinning through all those particles. We say those particles don't exist. They're there. It's got to scrub through it. It's getting hotter than hell. And guess what? We got the same thing. Only we got an issue. Because we're expanding our balloon that surrounds the Earth. That's why the weather is getting really tumultuous, and weather patterns are shifting, tons of rain, extreme amounts of hail, tornadoes, all that stuff. That's a product of the expansion, to my mind, of the atmosphere around our planet scrubbing through as well. And guess what the temperature is out there? The temperature out there is thousands of degrees. And they say, yeah, but there's no density to it. There's nothing out there. It's very hot, but it's thin. No, it's not. It's hot out there, but it's just the white part. It doesn't have any density, correct. Just below that part is the dark matter, and it's minus 100 and something degrees. So you go 3,000 above to minus something, 100 or more. Oh, I know it's more than 100. And that zone is the dipole. The dark is here, the white is here. The white is hitting, and the dipole nature of this creates the black layer. And it's, like I say, minus something, 100 and something. And then it gets hot again underneath, and that's where we are in the warming up zone. And the moon reflects. It doesn't create any, well, I don't know, I can't say anymore. I can see some spots on the moon, I don't know what they're for. But anyway, when it radiates, it's very, very slow. That's the spring there. Slow, it's in the red range. When these come down, they can fast, or they can come slower. and you don't have a lot of blue. And so it just depends what the sun is kicking out at that exact time, what we get hit with. It's so obvious when you start to look at what's going on. It's the particles, and we're scrubbing through space spinning. And the part that faces the sun, so obviously it gets hotter and hotter and hotter. And as we get bigger and bigger and bigger, we scrub hotter and hotter. And it's more, violent weather. Okay, as always, I disagree with this. I'm going to ask chat about this. Are we ready? Here goes. If particles were made of dipoles and they were muons and electron neutrinos stuck together called a Dirac neutrino, and they could be split apart, causing the dipoles to separate, would that be considered fission? All right, let's see what they got to say.
This is a very creative and speculative idea. Let's break it down carefully and assess it within the framework of known physics. First, the components. Muons and electron neutrinos are both fundamental particles in the Standard Model.
All right, so the muons and electron neutrinos are fundamental. They're the tiniest particles in the Standard Model. They didn't realize they found them. All right, now let's continue on here. Well, I suppose I can't. I'll just read it to you. Muons and electron neutrinos, which I showed you, are the black and the white balls stuck together, which are Dirac neutrinos. They're fundamental particles in a Standard Model. A Dirac is hypothetically kind of a neutrino. No, it's called a Dirac neutrino. It has distinct particle and antiparticle states. No, it's a dipole. As opposed to a Majorna neutrino, which is its own antiparticle. The Majorna neutrino, I believe what they're talking about is where they're coming up to the energy of an actual photon. So there's flavors of them. But I'm not sure about that. I don't really care about the Majorna. It's not important to understand that. Now, dipoles in general physics are systems with two poles, yes. Electric or magnetic, the same. There is no difference between an electric or magnetic. Such as positive and negative charge pairs, yes. They're called gluons. Now, your scenario. You're proposing a model where a particle called a Dirac neutrino is made up of a muon and an electron neutrino, which are held together like a dipole. Exactly. And this system can be split apart. Here's how this idea lines up or doesn't with known physics. Are neutrinos or muons dipoles? Together they are a dipole, not one or the other. They're two separate charges, the black one and the white one. No, neither muons nor electron neutrinos are dipoles. They're two poles of a dipole. They're elementary particles as far as we currently know, and they have no real clue whatsoever. They're not composites. Yes, they are. The idea of them forming a dipole structure together is speculative and not part of the Standard Model. Well, it's not speculative, and it should be. It's dipole electron flood theory, so the Standard Model is gone now. Now, is combining a muon and a neutrino into a Dirac neutrino viable? Not in current theory. Well, that's because they don't know dipole electron flood. A Dirac neutrino is a type of neutrino that includes both the left-handed neutrino and the right-handed antineutrino component. But it's still a single neutrino species. It's a dipole, not a composite of other leptons. Yes, it is. It's the white and the black. It's the muon and the electron neutrino together, stuck together. A muon is much heavier, which is true, and a different lepton flavor. That's fine. They're glued together. The black one is the carrier. It's heavy and it doesn't fall apart. Combining it with an electron neutrino would violate conservation laws. We see, we got to follow that law, and they got to follow the standard model. No, you don't. Some very new physics beyond the standard model. Yes, it is beyond the standard model, 100%. If this object were split, would it be fission? No. Yes, it would be. Not in the standard usage of the word. Fission usually refers to splitting of a nucleus. These are things that are in the nucleus. When they split a nucleus, what they get is these little particles fissioned out as the energy. We don't have to. We split the one right together, and it just makes energy everywhere. So they're saying fission usually recurs to splitting a nucleus. We don't have to be gigantic nucleuses into smaller nuclei, which are these. Energy. Some of them can be big and they can really hurt you, but most of it's going to shoot. All of ours is shot out from light, so ours are like this size. There's nothing to them. All right, your scenario describes dissociation, yes, of a composite particle, yes, which would be more like decay. Yes, well, it's not really decay, it's just separation, or dissociation than fission. You call it anything you want. Fission is to break two things apart. What would this idea be considered? If a muon neutrino dipole somehow formed a bound state and could be separated, it would be a new composite particle, sort of like a hadron. Separating it would be more like breaking a bound state. Yes, maybe analogous to splitting a positron atom. Electron and positron bond together. Well, all of that's not correct, So the process would be better described as dissociation. Call it anything you want. We broke it apart. Your concept is highly speculative, not ruled out by logic, but not supported by current particle physics. Yes, it is. If such a dipole state existed and were split, it would be called dissociation, decay, not fission. The idea touches on interesting ideas, interesting area of physics, commonly, especially composite particles, and the nature of neutrinos. What's fusion? If they came back together, they were separated, they were black and white. When they come together, all right, as you know, I claim to understand subatomic nuclear physics. And from the light experiments I did long ago with Rod Warren, we could see light accelerate, which is not allowed. We could see light separate between the black and the white. If you can see these black and white photons, they break apart and then they come back together. We could see the Higgs fields, which is the same thing that CERN and Fermilab and all of them look for. And then we also saw this one particle, that one single particle. Now, I claim to be able to explain virtually all atomic interactions. You have to be able to. If you can't, then whatever you're thinking is probably not correct. So you have to be able to understand all of them. Now, I got to the point where I can show these different light particles, acceleration, reverse electromotive force, literally the same exact thing that happens in an atomic bomb. The black and the white separates. Normally they're like this. The black and the white like that. But when they concuss and explode and blow up so violently, the white leaves the black and showers. And that's exactly what you see. That's an electron shower. That's the cat's meow. That's what they're looking for. And we did it strictly with light from a laser through a venturi, which crushed this field, which wants to be this big coming in. But there's a whole batch more of them. They're all over the place. They're everywhere. You just don't see them because they're not accelerated or pushed back against. The only time you see them basically is when they hit something. Now this is like hitting a cloud of particles coming back at it because that's what's happening. And I will show those clearly. And that's why these are showing up. They're here. You just can't see them. This field is being crushed down till all we have is a particle. And now they're all trying to fit through that venturi, and they can't fit. And it's just a gigantic explosion. So the black separates from the white. That's fission. That's fission. They come back together as fusion. Now, this is on a subatomic level. When they do fission and fusion, they break apart big bombs of things like this, which are stable, let's say, semi-stable. They're really not stable, but let's call them stable. And when they implode them and then they explode, they just come out in bits and pieces. And then they reform in stability, but the remainder of it goes into this white shower of energy. That's the nuclear explosion. And then they come back into chunks like this, which are heavy duty jobbers, and then they just smash over houses and all that. But this is what burns everything. It just burns everything. And I show that. Well, I'll show it to you right now. Okay, my outstanding friends, I am now going to try to explain nuclear bombs, because I have to explain how that total amount of energy can be created from such a small package in relationship to the amount of devastation they do. And I have to show dipole electron flood theory can show that much increase in energy. It's going to be hard to do. Okay, my friends, I've been claiming I understand the anatomy of the dipole particles that make up protons, neutrons, and virtually everything. I call it atomic vapor. And they condense into balls, which they call protons. And they're for some reason stable at a certain number of particles, which appears to be about 1839 or 1840, somewhere in that area. And each particle is made of these black and white ones together. However, we were able to divide them, which I will show you in a moment. But this is basically what now replaces the standard model. And it's these two particles are the only thing that exist. And when you have 1839 of them together, you have a proton. Anything lower than that is unstable, and it's just explosive. All right, that's when you get your energy, is when you try to separate an atom, which is the breaking up of an atom. That's what atomic explosions are. Now, what happens when you explode it? You end up getting these little things out of there, light primarily, and then chunks of these still added together, which are like hand grenades, very, very damaging to any living thing. And then you get enormous amounts of flash and light and electrons. That's really what we would always consider an electron, because we don't know about that dark matter. Dark matter is attached to the electron. Everything that is an electron has weight. If you add heat, which this makes heat, and you add that to something that doesn't change size, it will become heavier. You think, oh, it's going to raise up in the air. No, it won't. It only raises up in the air if you just put in the gas, all right, which is this part, all right, and it swells up. Then it raises up in the air. But if it doesn't swell up, it just sort of migrates in and sort of fills in. And then, because things can travel in and out. That's what temperature ranges are. It's just electrons travel in, electrons traveling out. I know this for a fact because I did weights and measures. Well, I didn't do them. I had weights that had to be validated by the weights and measures, and we had to leave them overnight because they had to have the same temperature as a room. If they didn't have the same temperature, they had too many electrons, they'd be heavier. Very, very, very tiny amount, but weights and measures could detect that amount. And I asked him, I said, how could you possibly see that? And he said, we can tell. He said, and we don't know why. He said, but they do change weights. If you bring them in and they're warm, and we put them in there and it's colder in there, it's going to be different. If you bring them in cold and it's warmer in there, it's going to be different. And I said, well, how could you see that. And he said, well, we see it, and we think it has something to do with the air currents circulating in there. They didn't know. They had no idea, and they still don't know. I don't think. But they know that it gets heavier when you add heat to something. It's not unknown, because these have weight. The black part has the weight, and this is heat. When you put two back to back, it bounces. It doesn't go in and attract and sort of hang around. They bounce off. That's what light is. Photons. This is heat. That's photons. Electricity is just the white, all by itself. The blacks don't get through, and I'm going to show you how much electricity you can get from what they call electron showers. Let me just show you that, because that'll knock your socks off. All right, there's a fancy little Greek-looking U, but it's still a U, and it often represents the potential energy in physics. Well, yes, it does exactly what it represents. So U is energy. Potential energy means I can use this like a battery. I got energy here. I'm ready to go. That's potential energy. Kinetic energy is when you're making something do. So you're using the energy. But potential energy, that's what you need, like a battery. So U is potential energy in physics, a common notation indicating stored energy due to an object's position or configuration, like electric charge. The total mechanical energy in a system is the sum of its kinetic energy, where it's actually doing something, and then the battery's still back here, is its potential energy. So let's think of it in electricity, because basically everything is electric and magnetic. So the total mechanical energy, that's all the mechanical energy is capable of, is in the system, is the kinetic energy. So the wheels are traveling and you're going uphill, and you're using some of this energy, and it's potential energy, which is the battery. And that equals the total energy. Energy is kinetic plus the energy that's being used is potential energy. The stored energy. So I hope I said that right. But anyway, it's both what we're using right now and what we have available. It's just like a car. How much energy do you have in that car? And guess what? If you have a car that's electric and it weighs 4,000 pounds and it can go 600 miles on discharge, it'll still weigh 4,000 pounds when you're done driving. No change, basically, to speak of. There may be a nanogram, and there will probably be, but not, almost undetectable. And I've seen them doing the tests on this, and that's exactly what they have found. They see no change in the weight whatsoever, because they weigh probably by the pound, that type of thing. You're not going to see any weight change whatsoever. But if you take gasoline and you put enough for 600 miles, and you got 30 miles to the gallon, every gallon weighs 6 pounds. So just figure it that way. You use 10 gallons, just 60 pounds. 60 pounds of gasoline. Otherwise, electricity, zero. No emissions, no nothing. How do you get that electric energy? And what is electric energy? It's the white part. It's the white part of the particles that I'm showing you. That's the electricity. That's what we need to harvest. And I think we could do this. All right, I just showed you what potential energy is, or energy, kinetic energy, potential energy. It's energy. And this depends on the number in the showers, the maximum energy. So down here, we don't have any real showers. The number of base tracks of the shower is very small. And then it starts to get big, and then all of a sudden, right at the venturi, you get the shower. And this is the number of base tracks. Down here, you only have a few base tracks. All of a sudden, billions. Now, and this is the showers. This is the energy. That's from down here, very, very low energy, almost no energy, up to an energy that's just off the charts, instantaneously at the venturi, because that's where the shower happens. And this is the shower right here. number of base tracks of the shower. As it comes through, it starts to build up, build up, build up, build up, and then right at the venturi, right through the roof. I believe that's precisely what I just showed you. So what ends up happening? A very low amount of energy starts here, and then it comes out, I'm sorry, a low number of showers, which is the electrons, bumping into each other, building bigger, 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 because the blacks are smacking them. They don't take this into account. And then this is how the energy rises instantaneously at the venturi. And as you saw, this is the venturi, right there. And here is just 100% white energy. All right, it started out like this, boom, 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 boom. This is black and white, the photons. All of a sudden, it sees the venturi, and venturi is it's an accelerator. It's known. It's not a mystery. And at that point, it goes so fast. When it hits there, it explodes at literally an atomic, subatomic bomb. It splits the black from the white. We have 100% white, which is just harvestable white. We should be able to harvest it right there into some kind of photodiode device that lets it go through but not come back. Zip right down in and use it. It's potential energy. At that point, it's potential and can just be used as kinetic energy. And it should be something you can hold around and you carry around in your hand. If you get that kind of an increase in particles and energy, the U is the energy. If you get that kind of an increase from this kind of energy down here, which is very, very little energy, this is the maximum energy at these showering events, and we're getting some energy here, and then at the venturi where it's just nothing but white. All right, here you're spitting off little bits of white, little bits of white, little bits of white, and all of a sudden, zip, nothing but white. And that is where your energy is. So it's hundreds and hundreds of times the input energy, at least. And it appears much more than that. See, the problem with the big colliders is they need these big facilities, proton-proton collision. They're creating hadrons and all that nonsense, just decaying this and that, creating large flux energy, neutrinos. And they want to get down to the neutrinos of all flavors. Well, we're down to the actual muons and electron neutrinos separated. And then they say the energy of these neutrinos interacting is a few hundred giga-electron volts to a few trillion electron volts. That's staggering, because you're starting with, I would probably say, maybe hundreds of millions, but not hundreds of billions, and certainly not trillions. So what is that? It's an increase in energy. What is that? Free energy. All right, here's what's happening with CERN. They're taking huge things like this, and they're hitting them, trying to hit them head on. And when they do, they get all this debris, all these little debris things, which are the particles we started with, are these little bitty particles. So we already were way down to those tiniest of this debris. And we don't have to deal with all the big debris because we started with, that's the biggest we ever got. That's what light is a photon. So when these come together, they usually do this. They won't hit into each other's fields and bang. I really can't push that together. Watch this. Whoops. This one here is a strange magnet, but it's, watch. You see that? That's about as close as I can get them. And it pushes out off hard. So they very rarely, now see, I have this configured. This is a backwards magnet. Watch this. It shouldn't do that. Ooh. Anyway, what's going on here is they're getting a bunch of debris. We're getting the particles that you want to get, because they need the little bitty ones to harvest. That's the energy. And I can show you that the black ones push the white ones. That's the energy you want to put in your battery. You don't want the black. The black's got to stay back. And that's what we were able to do right here, right at the venturi. No black gets here. Now, if we put a harvester right there, we might be able to have something we could actually use. So what this shows in the map, right here, this is what it is. If you can get that to shower, in these ultimate amounts of showers, your energy level goes right through the roof instantaneously. So what does that mean? That means you have this available to use right now or to store and continue to feed. What would we have to do to make a handheld device? I don't know, but I can show you what my concept would be. This goes back a long time. I've been showing this stuff, over 10 years. And they started to pick up on these particles that are inside the proton, like linked to, like never before. This still goes back a couple of years ago. All right, this is just my concept. It wouldn't take long to figure if it's going to work or not. If we can harvest more energy here than we started with here, then we should proceed. If not, we should just forget about it. But if we're sending light through here with a laser, and you have to experiment. You can't do this in 10 minutes, or you might be able to in 10 minutes. But it's shooting through here, through a venturi, and the starting, let's say it took 5 watts of energy to get this laser to go. And that's, they don't take much energy whatsoever. And if we could come out of here with 500 watts, 100 times more, that would be pretty good. Because then you could take that energy, feed back to keep this going using part of it, and the rest you feed off. And I'll show you something you might even be able to carry around in a little lunchbox. Because what you're going to get here, you have to harvest right there. You got to harvest it right there before it comes back to the black. And then it will go anywhere you want it to go through wires and so forth to get back to another bunch of black. That's all the white wants to do. It will seek black like a rocket ship. That's why electricity, well, lightning. Lightning is nothing more than the white part. Right to ground. It'll go right through you. You put your hand up, it goes right through you, you turn into ash. This stuff is just deadly powerful. A good, strong motor with electricity just is unbeatable. Very, very powerful. But you have to be able to get straight to that white. And again, it has no weight whatsoever. This event right here that I'm showing you, I'm going to show you atomic bomb blast. This is literally exactly what happens in atomic bomb blast. It's so powerful that the white is pushed forward ahead of the black particles. They're separated at this point. All the white is ahead of the black. Well, not all of it, but most of it. And that's the wave that's pushing this out. This is just like an atomic bomb. Now, there's going to be a house right here. And we're going to see it in slow motion. And the house is going to vaporize. It's not going to move. It doesn't move whatsoever, not even the tiniest bit of movement. It's just smoke comes up, and then all of a sudden the black hits, and boom, it's all over. I'm going to show you that. This was from the nuclear bomb blast, and some of that footage is oh man, is this stunning. All right, this is from Adams Central, and it's about the atomic bomb blast from the Teapot Dome experiment. This is footage from the government, and they're showing what happens in an atomic bomb. Now, this is extremely slow motion. It's going to go off, and you're going to see the house lit up brilliantly, and it doesn't go anywhere. It just smokes up. I'm going to just play it. Watch. Didn't go anywhere. Didn't go anywhere. Boom, there it goes. That's pretty strange, isn't it? Now, not only does it not go anywhere, and everything smokes up. You see the poles, the wires, just smoke. Everything that's combustible, that's not going to burn up because those are they're metal tanks. The transformers that don't look like they're burning, but metal doesn't have the same combustibility Now here's something that's even strange. Well, not stranger, but here's what happened. We saw only the white hit and smoke everything up. So white has no mass. All right, can you agree with that? There's no mass. It didn't push anything. No mass. I don't know how you could. There's no mass. It just smoked. This is all the mass. Boom. And here goes the house. Now watch what happens. This is the blast, and it all comes back. Well, not all comes back, but well, you just watch what you see. Let's go back here and see the blast again. Smoke, 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 blast. Watch what happens. It turns around, comes back. You see all this rush? It's turning around and coming back. Boom. That's very interesting because it created virtually a hole in the atmosphere that had to sweep back in. It's a depressurized zone, let's call it that. Everything has been emitted. Had to come back. All right, this is just beyond cool. This is the atomic bomb. The black part is the thing that knocked the house over. The white part was ahead of it and burnt the house up. Well, why is this so concentrated white? And what is this? This is all part of the same event. This is preceding that. Well, Rod caught this at the explosion, and this is called Whistler waves, and they make a tiny little prrr, and he told me he thought he could hear a crackle every now and then, and I think this is when it happens. Now I'm going to show you this in atomic bomb blast, and we're going to see the bomb go off in the distance, and we're going to hear brrr. That's these, they call it Whistler waves, and they're in the audible range. They're not down here in the light range. They're wider, and they have no black with them that I can determine. They appear to be strictly the white bumpy part. So let's see, let's hear it. All right, listen to this now. I'm going to turn this up very loud. Now, the bomb's down here. We're, I don't know, several miles away. And so we're not really going to hear, well, let's see what we do here, because here it goes. All right, did you just hear that? Brrr. We can see the brightness. There's no bang. All right, we got to wait quite a while for the bang. I'll bring it out to where the bang comes to us. All right, we're way off in the distance here now. You're trying to catch up with the white one. See, that's finally it hits us, and this is way up in the air by then. So that's the black part hitting us, and before that we hear the and we can see the bright. But that's an atomic bomb. It's like the size of a BB compared to what they have now. It's just stunning. So that really, that's everything. That's the atomic explosion through the venturi in this case, and this is all that high impact stuff working with some black. In our other case, we just squirted the white through. We didn't have any black. That makes it way more efficient. This is not efficient, but it shows us exactly how the thing works. And that creates these bumpy, audible, the Whistler waves. These are things, I'm telling you, these things exist. And this is the flux, the energy. And it's massless. And then the mass, which is pushing this massless, they used to call it the boson carriers. This was the carrier. And I agree with that. It's the carrier. But if you do it right, you don't even need a carrier. You can slap the white. I'll show you. All right, we know we have these particles, which are the photons. There's no question about that. And as they come forward, the bottom one, or whichever one is in front, starts to glow. As it glows, it gets brighter and brighter, and then it flips, and the other one comes and takes over. So that's what creates the muon wobble, they call it. Now, we know for a fact these were glued together. There's no question about that. There's zero question. We know they came apart. Of that, there is zero question. Zero question. They are apart now. And the only reason we can see the black is because it's sitting on top of the white. The black is the dark matter. It's dark matter. We've never seen it before because it's inside. It's like this. This is the structure of a true proton. It's like that. And you look at it and you shine light on it and it shines back at you and you say, yep, no dark matter there. Well, guess where it is? It's inside. Right there. So if you can get underneath this layer, whoops, and you're down in here where you have dark matter, you just can't control it. You get down into this range where we are, which is just one of these and one of those. Well, actually it's two of these and two of those in a photon configuration. And then we smash them. No question whatsoever, zero question. The black has separated from the white. And all we have is the white. Well, why did that happen? And can we show it over here and understand it? And I think we can. And it's certainly shown. And it is the black muon, which goes sterile by itself. It stays just like that. It's still well configured and massive. And the electrons go into the shower, which have no mass. Fully understood. This is the particle back here. It's one of these particles that is the photon here. And it's traveling like light does, just going forward, having a nice time. And then all of a sudden it says, wow, look at that. It's like a venturi up there. It's a suction device, just like the nozzle on your hose. And you have a certain amount coming at it. And when you restrict it, it just creates a lot of energy. It squirts way, way, way out. Or rather, it's dribbled as this. It squirts way, way, way out. All right? Now, normally there would be less of it. But because we are slapping this with the black that can't get through, it's crushing all these fields down inside. So not only are we getting the fields that would normally go, we're pushing everything in front with a slap. And it comes out the back here, just squirt, 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 squirt. I mean, a bazillion times a second. And that's so energetic that the blowback creates enormous, enormous reverse electromagnetic fields, which are these going this way. And then they've just been announcing, oh, we can see light going backwards. I've been showing 10 years. All that is a bounce back. It's no big deal. It's a magnetic field going backwards. This is the big deal. All right, I don't see why you couldn't have something like this, which you have every kind of outlet you can imagine in there. Any kind of voltage, any kind of whatever you want. Have thousands of these little tiny lasers inside this, all pointing at little venturis, and a lot of design capabilities, which is this. This here is right there. That is this. You put a harvester right here coming down, which is this photodiode, where it goes through one direction, can't come back out. Energy comes back down here, feeds batteries, motors, whatever devices, and then this is basically a floating ground. So we can come back here and keep that laser going. And whatever devices we want to put in to use that energy, it's potential energy at this point. It's that U factor. And you should be able to carry it around in this and be able to, I don't know what you could power with that, but it's a lot of things. And it would totally off the grid. Once you start it up, it just never stops. Basically, you know, there's some engineering here, but it's certainly worth a try. And all we have to do is try to see if we can get more energy out this side, harvested somehow over here. almost like with a solar panel. But they have these new things, the perovskites. They're very, very absorptive. They're thin-filmed metal. Here's the deal. Basically, every one of these vibrates at a different frequency. So you need a thin film of all of these going deeper and deeper and deeper into the frequencies, and you'll absorb all of those different frequencies. It's not that hard to understand if you understand it. And I think they're starting to understand. You just spray on the different frequencies of metals or whatever, semiconductors. And you might have to have a lot of silicates in there. Silicates, semiconductors are built around silicates. So there's a lot of engineering to do. I'm not making it sound real simple. Maybe it's not simple. I think it might be, but that's what we got to check into. I think it's worth a try. All right, I showed you that the electrons shower from small to really great, the base tracks of electron showers. The muons just bounce right off, which is precisely what we see in our experiments. The muons bounce right back and the electrons shower like crazy. But we didn't have to build $1 billion machines to do this. This is very, very inexpensive. Now, the outcome, I would say, could very well be this. Just little lasers inside there with these venturis and a collection device in here. You don't even hardly need batteries, because if it increases the energy the way they're saying it does, if that's true, if you have this little bit of energy coming in here, just a little bit of energy to drive this, and then it separates and goes up to here. From this little bit of energy up to that energy, that is staggering. And here it is right here. The shower bit, they come in and they start to shower, and then right up through the roof, which gives you unlimited amount of energy, I would think, because you should be able to put, I would think, hundreds of, or thousands of these little lasers inside something this size. A few regulation devices, and you bust it out into whatever you need to plug into. When I say bust it out, that's put it into a bigger, you need to have some kind of size in here if you're going to use a lot of electricity. You can't put through a tiny wire a lot of electricity. I don't care how much electricity you make. At a certain point, that wire is just going to melt or explode or whatever. So you need a bus, basically they call it, which is a metal, big copper plate, something like that in there, that has enough mass that it can move enough electricity without resistance or very little resistance, so it doesn't overheat. There's design engineering stuff in here, and there might be some weight to that. I don't know. It depends on how much energy you need, how much energy you're going to use, how quick you're going to use it. I would imagine a car is going to have you'd have to have something pretty heavy duty. I don't know. I really don't know. If it was taking it out right away and you had enough of a conduit to get it out, you might be good with something that small. This is all unknowns at this moment, unknowns. But I think it's certainly well worth a look. If and these are my little doodles. I didn't make that doodle. That is not my doodle. All right? That is not my doodle. And this is not my doodle either. Up to a few hundred billion electron volts to trillions of electron volts. But they need to get down to the neutrinos where we started. And we're in the handheld device. They're in, huge things. And now they're doing this to find these neutrinos, which I'm showing you. These are neutrinos. You see this right here? What does that say? Muon neutrino is the black ball, electron neutrino is this. They can't find these. They're doing a deep underground neutrino experiment right now, costing us billions of dollars. And I've been showing these for 10 years, and they are here, and these are neutrinos. And if somebody can come up with a reasonable discussion against it, I certainly want to have that. And I want it anyway. I want to be able to say, please explain what you see if it's not what I'm saying it is. And if it is what I'm saying it is, everything's different, because dipole electron flood theory now rules the day, which it does. And there's nobody can stand up against it. Nobody can stand up against it now. And that's what I'm asking for. And again, this is Fermilab's pictures 10 years, or 12, more than that, 13 years ago. Don Lincoln put these out, and I contacted him. I said, I got your picture, I got your particles, and we used light, and boy, I'll tell you, it did not go well. And it's time to revisit this, because this has been a very, very contentious dispute. He's a public guy, he's a public servant, spending our money, refusing to examine this. I mean, I'm talking about refusing. Absolutely, he said, I will not look at anything you present to us. And I'm blocked from speaking to him. So, he's supposedly working for us. I don't think that's the case, my friends. That's just my opinion. Anyway, I don't see why we shouldn't start looking at this. And these are neutrinos here, Dirac neutrinos, same stuff. They just don't know what they're looking at, because they don't understand dipole electron flood theory. It's just everything's made out of dipoles. Every proton at a certain number of particles is stable, and that's 1839 approximately in my model. It could be different, but it's going to be a whole batch of little ones. And then when they all break out, each one of them has its own region. And instead of being tiny little ball together, being comfy together, coating that black, they go off on their own, a black and white on its own, and that's called a heat particle. And they get hot, and they just explode into a bomb. And when you hear hydrogen go off, just hydrogen itself, the explosion is stunning compared to, like, a firecracker or something like that. But hydrogen gas, along with oxygen, is the explosion. Well, I guess I should show you. All right, this is on a channel called Alex Smith, and it's hydrogen-oxygen balloon explosions. Now, watch what's going to happen here. He's got hydrogen gas and oxygen gas in the same balloon together, and he's going to set it off, and he's telling the kids to keep their mouth open because they could blow their eardrums out. And he's in an auditorium. Now listen to this. Here goes. Let me open this up.
Too loud for you. Keep your mouth open, because then the pressure in your mouth will come outside your
Yeah, the kids are freaking out. Now, what do you see? What is that? Is that just smoke? No, that's not smoke. That's water. That's water. He's got H2O2. Ends up compressing down into H2O gas, moisture particles, and an enormous amount of explosion. Well, what was the explosion? Well, how did it make that big bang if we just ended up with some water? It lost one of the oxygens. It was H2 and O2. One of the oxygens turned out into particles. And that's why it was so explosive. I mean, combustion is, I don't want to get too deep into it right now, but it lost oxygens, and instead of them being oxygen in big chunks, they turned into oxygens into little particles and gas, a big expansion. Whenever you have that, it's an expansion. So what happened? The particles of oxygen expanded, because we ended up with the water. The water's still here, H2O2, I mean H2O, but one of the oxygens is gone. And that's what made this, because every one of the little particles in that oxygen expanded apart, basically. And that's why you had such an absolutely enormous explosion from just these little that little balloon. Okay, let's discuss these statements about the tether. I asked, how much energy did they create using the tether experiment, and what happened to the tether? How did it break? Great question, Roger. The NASA tether experiment you're referring to took place during the STS-75 mission, Space Shuttle Columbia, February 1996. It involved a dramatic and scientifically valuable incident. Well, we know that they deployed that tether, and it was supposed to be 20.7 kilometers long. And it almost right at the very end of its deployment, it snapped, and the satellite drifted away. So to me, I say that the tether itself snapped right at the satellite because of an overload of electrical conduction, because this was an experiment to harvest electricity. Now let me read to you what they have to say, and of course I will have my comments. Alright, you did see the tether glowing like crazy a mile wide when it's just a strip about the size of a feather. Now, so they were trying to harvest energy to see if they could. So at the satellite, they had like a voltage meter to see what's coming in, how many volts, how many amps, all that business. Now, it says the tether satellite system designed to demonstrate how a 20.7 kilometer, which is 12.9 mile long conductive tether, conductive means it accepts like a wire, okay, could it generate electricity by moving through Earth's magnetic field in orbit. Now, the electrical output before the breakage, so it did finally burn open. Now, what did they collect? Well, it generated over 3,500 volts. That's a lot of voltage. That's extreme amounts of pressure. Voltage is pressure. It's like a hose. You turn it up more and more and more and more. Pressure squirts further and further and further. That's what voltage is. Now, there's another part, is amperage. Amperage is the number of particles. This is, you could have a tiny few of them, but they're going bazillion miles an hour. It's still high voltage, low amperage. Then you can have amperage, you can have low amperage, you can have high amperage. High amperage means you're going to need a big conductor. If you only have a small conductor, it's going to explode because there's too many particles going through at the same time. And that's what happened to the tether. Now, the system generated 3,500 volts. That's a lot of voltage for a tiny wire. It was producing an electrical current of about 0.5 amps. That's a fairly good amount of current for something that small. And I'm sure it was only producing it because there was so much resistance to the flow. It equates to a power output of approximately 1.75 kilowatts that had potential to produce up to several kilowatts. So if it was fully deployed, it wasn't fully deployed, but it was overloaded already. That's why it burned through. I'm absolutely certain of that. In my mind, I could be wrong, but I don't think so. So yes, the tether did successfully generate power, and it would have generated a lot. The tether broke when it was almost fully deployed. It didn't break, it burned. Now, it was about 19.7 kilometers out, and it was planned to go to 20.7, so it was a kilometer short, and it popped. The tether had a tiny flaw in its insulation. They don't know that. There's absolutely no way they could possibly know that. Zero. Think about it. Just give it a little bit of thought. Oh, yeah, well, we know there was a tiny flaw. No, they don't. It was too much energy. It says likely, no, there was a tether. The tether had a tiny flaw. No, it didn't. likely a pinprick size hole or abrasion. As current flowed through the tether, it was so much invasion, it ionized the surrounding gas, low density plasma in space. That's why the whole thing was glowing like this, because it was attracting all of these white particles to its darkness. White particles want to attach to matter, and there was very little matter in that space. And this will take, they all were just attracted. So it was like the ionized surrounding gas around it. Yes, it was an ionized surrounding gas. So I agree with that. It created an electric arc, basically a short circuit between the tether, conduit, core, and the surrounding plasma. Well, yes and no. The arc burned through the tether, melting it, and caused it to snap. And I imagine it snapped right at the satellite, because that's where it was harvesting and collecting the energy. No, the satellite floated away. So I believe the satellite just floated away because that's where the connection was lost. The mission was cut short, but the event provided a wealth of data. No damage occurred to the shuttle itself. They were 70, 80 miles away. The break was captured on video, showing the tether and satellite drifting in orbit. The footage led to UFO conspiracy theories due to the strange shape scenes, but those were later confirmed to be out of focus debris or ice particles. I disagree with that totally, as I think I have shown you. Now these are the details of the mission, Outcome, tether snapped, satellite lost, experiment cut short. I see this as total speculation to what they're saying happened, and I understand why it was absorbing so much electricity. It's just nothing but saturated electricity out there, and it's looking for something, a ground basically, to attach to. Because out there, that would be its ground. It's just like the Earth is ground for heat, light, electricity. You take electricity, you put it to ground, right to ground. This is nothing more than ground in space. They call it a floating ground. I'm not kidding you. It's a floating ground. The electricity wants to get to it, so it'll absorb. It's floating ground. And this is floating in space. You see? What is a floating ground? A floating ground in electricity refers to a ground reference point. It's not electrically connected to the Earth, which is normally ground. When you say make sure it's grounded, you make sure it's onto a water pipe or something that goes in the ground. I have lightning rods on my house and 10-foot copper rods in the ground because I'm way up on a hill and it sweeps up like this and was charging up electrical current, electricity on my house because it's kind of steep on that hill, and I was having lightning problems. So I had the lightning rods put in. I've never had another issue. Lightning rods don't work the way they think, where they attract lightning. They keep you at a certain potential, which is basically ground level. It's a little bit different concept than anyway, that's a whole other issue. Now, so what is a ground in the electrical system? It's just you got to get the electricity back, the white, back to this floating ground. It floats. Its potential can vary depending on the circuits it's in. It's not fixed to 0 volts relative to the actual Earth. It's not at the Earth, but electricity goes through and comes back. Virtually every handheld device uses a floating ground. See, I'm not inventing the wheel here or anything. I do all handheld electrical devices use a floating ground, yes. Almost all handheld electrical devices that are not plugged into the wall use a floating ground by default. They have to. They have to have that electricity going through their device and back to its ground that's portable. So I'm not inventing anything special here. This is just what it is. We just need to harvest that white energy, and then we just have a floating ground and the case is closed. As far as I'm concerned, I don't see any reason not to investigate it. Okay, my friends, here we go. First utterly alone black hole confirmed roaming the cosmos. This is just out short a while ago. And this is illustration. This is not real. All right, well, let me show you something that is real and looks quite similar. All right, this is from 2015. The Russians were up there in space and they took a capsule of a vacuum chamber up there so they could suck everything out of it. And then they took all these little charged dust particles and they let them seep into this vacuum chamber. And they went in and they went woof, woof, woof. At first they were all just crazy. And then they started to coalesce around this black thing and sort of, you could see them sort of pushing all the black stuff together. Now, and all of the dark particles are in here, and you can't see them. You're not seeing any light reflecting, absorbing, emitting, but you can see the other ones around it reflecting back. This is still a source of a mystery for me, why we see nothing at all here. But that is the nature of dark matter. Now, is it the only reason we're seeing this is because we're shining light into it? I believe that's the case. And the light will not bounce off, which means it doesn't reflect. Nothing emits from there. That's what a black dark matter is. And the only thing that attracts it, is attracted to it, is the white. The black seems to be able to, you know, like there's thousands and thousands of little black particles in here, and there's thousands and thousands of white ones that are trying to get to it. And it keeps getting crustier and crustier as it lasts. Now, they freaked out. This is during the experiment we contacted the Earth guys who couldn't believe it either. Now, I had my eye on this pretty close. One of the guys from Max Planck locked himself in his office for 3 weeks because he just freaked out. He said, nothing makes sense anymore. And they're right, nothing does make sense when you start to look at what really happens with the particles. All of this was just dropped as far as I know. But I did contact the Russians, and I contacted Fermilab to show them our research and this, and what they found at Fermilab. They're same particles, because this is the Fermilab stuff. This has all the weight. I agree. It's a dark particle, has all the weight. One size fits all. I agree. They're all the same: black, green, red. I mean, red, green, blue. We've seen them all the same size. And then the glowy one can get big and get small. You can see it, big and small. And together as a box, it's a photon. They have found those in their collisions. They've got them too. They see them, but they just don't know what to make of it, because there's all these other little things hanging around there that are all busted up, and then there's X particles, or big, huge chunks. So they have a particle zoo. We started with that, so we can see these little buggers, and we can see the black ones drift away too. So, you know, I'm not making any outrageous claims here. I think this should be examined, and we can see that the green is much more energetic than the red. You see this? That's the green coming through at the same time with the red, and the red is barrel rolling. That is unheard of. They spin up and down spin. Just ask any particle physicist and say, well, what is the spin? Well, it's up and down. What does that mean? Well, it's up and down means energy is up going this way or down going this way. That's all. Polarized towards the Earth. And that's what we found on our experiments too, except this, where we forced both of them through at the same time, through the same venturi, which made that barrel roll. And then reconcuss the green out here, because it's much, much, much more energetic. And it's also, you know, it is the same photon as all the rest of them. Green is the same, as the blue, as is the red. They're all the same. No difference. Just the speed of the spin, and it is spin. It's this. It's spinning this way. All right. It's not flapping like a wave. It's spinning, and as it spins, it creates these round fields. Well, let me show you something. All right, in my opinion, this is what we should be looking into. Here's the photons. All right, here's where they're coming in as neutrinos. They're gaining energy. See, they're sideways, and then they're flat like this, and then they go sideways, and then they turn into regular full photons, because the actual particle senses such a field in front of it that it thinks it hit a wall. All right, right here, this field is coming back at it, and that's the reverse EMF. Now, this is propagated by this pulsed red laser, and it's got to plow through all these fields. Now, Rod caught this just as it was starting its way through everything else. He said, get out of the way, get out of the way. And it is going to seek right into a venturi, which is directly in front of it. You see it? So here it is here. It's just starting now, but it's seeing this. And that's the only reason we can see anything here. There's other ones over here and over everywhere. But that's the only reason we can see it, because it's going to head directly into that venturi. That's the only one affected by the venturi. They're over here. They're everywhere. But the blowback is what creates them to become visible, just like this is visible because it's going forward. It's dim. You see these? Those are brilliant. You see that? They're all the same. You're just never going to see them until they hit something normally. This one here is going forward strong enough so it's pulling itself right out of its own magnetic field. That's just amazing to me. And right here, it just becomes visible along with all the rest of them because of the squirt back. There's fields back here that go way, 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 way back, because this is a subatomic nuclear explosion. The black has separated from the white, and it's this black and this white. And this is coming out of the venturi through here. We're looking into it, creating these Higgs fields. But the truth is, the Higgs fields were here going into it. So going in is light, which are nothing more to me. They look like Higgs fields to me. And then coming out of them, they turn back into Higgs fields. But in the meantime, there's nothing but whiteness here. This is the reattachment of the white to the black. And I have all this evidence to support what I'm saying. And again, these are the red photons, very slow, and they're just gaining energy. You see this one? This is an upspin, because the white is going that way. Well, the particle's going that way, and the white is in front. And it's flipped. Now it's a downspin. They charge up and flip, charge up and flip, charge up and flip, but always straight up and down. Even if it wasn't going straight, even if it was going this way or that way, it would still spin according to the Earth, the polarity of the Earth. And I can prove that by this. This is the green, much more energetic. And this is straight up and down, which is its normal orientation to the Earth. However, that particle is actually going in this direction. So why is it spinning this way? They always spin according to the Earth, upspin and downspin. That's what I've discovered. And here it is right here. It's going off to this direction. See it? But it's still spinning absolutely straight up and down. And these are the neutrino phases, the same as the red. There's no difference. Now the blue is not, you can't really see the blue like you can these. The blue is just too hot. It comes in, you don't even know that there's a photon here. It looks like a single particle. And then quite quickly, as it comes through, you see how bunched up it is? That means this is spinning like hell. And then all of a sudden it slows down. And it drifts to the left, which would indicate it was spinning to the right, and because this is one shot of the whole thing at once, same particle. And over here you can see there's a little taste of two there, so that it is also a photon, just like the others, but you almost can't tell. It's just way too fast. And it's just stunning what Rod did. I mean, I just can never thank him enough for his help. And he never got anything out of this, and he probably never will. But this is, without his help, I couldn't prove my dipole electron flood theory. And as far as I'm concerned, right now, this is done. It's a done deal. And we're showing exactly what they say. Electron showers create enormous amounts of energy. Anytime you see illumination, brighter, 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 means more and more and more energy. It's as simple as that. You just look it up, illumination. That's what they're doing right now at CERN. I worked, with the professors at the University of Geneva about this, about how we were able to see these particles. Because I go back a long time with this. Rod, the phone was a Galaxy S3 from Samsung. 2012 it came out, and Rod started doing all this stuff. And I saw it, and I went, wow. And from then on were years of experiments. And the end result was, I think we could be able to get these black particles to stay away, harvest just the white, which is just the electricity. That's all it is the electricity side. That is what generation of electricity is, pushing the white away from the black. Usually you have to tear it away and force it away mechanically. Windmills, turbines, gas engines, diesels, all that stuff. You don't need that. If you squirt it through the venturi, we know, there's no question whatsoever, we're coming out with the white particles that have no mass. Precisely what they say at Fermilab, and we can separate them. We did. And to not be allowed to speak, and if I put in, I said, why am I allowed to publish? I said, well, you're not really specifically not allowed to publish, but nobody's going to publish you because you're a pseudoscientist. We don't allow that. You don't pass peer review. You don't say what everybody else says. I said, well, I have the evidence. Doesn't matter. It's not peer reviewed. I said, well, who will peer review it? Nobody, because you're a pseudoscientist. And that's all I've ever heard. And everything I have is supported by physical material evidence. I'm a material scientist. I'm not a pseudo anything. And I'm doing all the things that they're doing at CERN and all the other places only for next to nothing. And that, I think, is the rub. And it's destroying the Earth, basically, for not looking into this. If we could have a handheld device like this, and you could carry these out in the woods and squirt water on fires and do all kinds of things, and camp out in the woods with one of these, just carry it around, you don't have to do anything to it. You shouldn't have to do anything. This is all solid state, cheap stuff. The Venturi, you got to tune that to some degree. Once it's designed, you zip, 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 they shoot billions of them off. Now, will it wear that Venturi out? Who knows? These are things, this is design things. That's very, very simple stuff. But within a matter of a few days, really, you could tell, on the other side of Venturi, are we getting more energy than we started with to make that laser shoot? If the laser takes 5 watts and we get 200 watts, well, that's not bad. That's what I said originally, I said 5 watts to 1,000 watts. Because they say, originally when I started looking into this, they were talking about if you could do this, you would increase 200 times. Now I think it's more than that. Because the last ones I saw were this. All right, here you come in here at literally nothing, just about zero, less than 50. Let's say 50. And up here you go up to 3,000. Well, maybe it is 50, I'm not real good with math, but you just divide 3,000 by 50, and that'll tell you how many times increase of energy. U is energy. Either you're using it, which just means it's kinetic energy, you're just using it as you're getting it, or is it potential energy, you're storing it. And I don't see why you really have to store a whole lot. You might be able to just walk around with one of those little things that weigh about 3-4 pounds. Everybody says, oh, that's what the old Sumerians used to carry around, these little lunch boxes, looking things, little handbags. Well, I can't say not, but you never know, because they have wristwatches and all kinds of stuff. heart monitors. Anyway, that's all I can say.